So what is optimum solution? An optimum solution is a feasible solution which optimizes the objective function. That means a function, sorry, a vector n cross 1 vector x1 x2 xn which satisfies all the constraints and all the restrictions and optimizes the value of objective function is called as optimum solution. Next is basic solution. So basic solution is obtained with the help of matrix method. In this we first convert the constraint in the standard form. So let Ax is equals to B be the system of m simultaneous linear equation in n variables. Or we can say Ax is equals to B represents the constraint of linear programming problem where rank of matrix A is m. And let B be the m cross m submatrix of A formed by m linearly independent columns of matrix A. That means we select m columns of matrix A which are linearly independent, then that is said to be matrix B. And we take a vector xb which is obtained from x. It is the vector of the variables which are associated with the columns of B. Then by solving the system of linear equation bxb is equals to small b, which gives xb is equals to b inverse small b, and we put other n minus m variables equals to 0. Then the solution xb comma 0 is said to be basic solution. It will be more clear with the help of example. xb is m cross 1 vector of decision variables associated with the columns of B, and xb is called as basic variables, whereas capital B is called as basic matrix. Now we go to simplex method. In simplex methods, there are some conditions which must be satisfied. First condition is that there must be at least two decision variables in linear programming problem. There may be 3, 4, 5 or any number of decision variables, but that there should be at least two. The right hand side of all the constraints must be non-negative. And third condition is all the constraints contain less than equal to sign. If any constraint contain greater than equal to sign or equal to sign, in that situation we cannot use simplex method. For that, different methods are defined. To explain the simplex method step by step, we use following example in which objective function is maximization of z is equals to 3x1 plus 2x2 plus 5x3. Subject to constraint x1 plus 2x2 plus x3 is less than equals to 430, 3x1 plus 2x3 less than equals to 460, 4x1 plus 4x3 less than equals to 420, and all the decision variables are not negatively restricted. So steps of simplex method are: first step is identify and formulate the problem. From our problem, we can see that it is already formulated, so we do not need to perform step 1. Second step is to convert the linear programming problem into the standard form and then convert it into the matrix form. So for that, I have converted the example used into the standard form. And method is already discussed when I will teach the different forms of the linear programming problem. So the standard form is maximization of z is equals to 3x1 plus 2x2 plus 5x3 plus 0s1 plus 0s2 plus 0s3. Here all the slack variables are multiplied with 0, so you may write or you may not write in the standard form these variables, but these are important for converting into the matrix form because it deals with the coefficients. So we do not forget coefficient of slack variables in objective function. So I have written it as 0s1 plus 0s2 plus 0s3. And constraint in standard form will become x1 plus 2x2 plus x3 plus s1 plus 0s2 plus 0s3 is equals to 430. 3x1 plus 0x2 plus 2x3 plus 0s1 plus s2 plus 0s3 is equals to 460. And x1 plus 0x2 plus 4x3 plus 0 S1 plus 0 S2 plus S3 is equals to 420. Decision variables were already non-negatively restricted, and slack variables are also non-negatively restricted variables. So here we can see that all the variables are not negatively restricted. Now we obtain the matrix form as these. In objective function, we write in row vector the cost coefficients, whereas in column vector we write all the variables involved in the linear programming problem in standard form. So first one is cost coefficient of x1, 2 is cost coefficient of x2, 5 is cost coefficient of x3, and so on. In next step, we convert constraint into the matrix form. Here you can see that first matrix, which is of order 3 cross 6, is matrix of constraint coefficients which are in the order of constraints. First constraint coefficient of x1 was 1, coefficient of x2 was 2, and coefficient of x3 was 1. Whereas coefficient of first slack variable, that is s1, was 1, and other coefficients of other slack variables are 0. So first row will become 1 2 1 1 0 0. In same manner, other two rows are formed, and column vector is again decision variables and slack variables are involved, and right hand side the constants are written. So constants were, in first constraint it was 430, in second constraint it was 460, and in third constraint it was 420. So it is written in same order: 430, 460, and 420. And since all the variables were non-negatively restricted, so here all the variables are mentioned: x1, x2, x3, s1, s2, s3. That is, column vector of variables is greater than equals to 0. Now step 3 said obtain the initial basic feasible solution by taking B matrix as identity. So B matrix is same as we have discussed in basic solution. So it is better to use basic matrix is identity, as we use xb is equals to capital B inverse small b. If we take capital B as identity matrix, so B inverse will also identity matrix, and it has property, it is multiplied with any matrix, then that matrix is obtained. So using this matrix, it is easy to invert and easy to multiply. We take initial matrix as identity matrix. So you can see from matrix that here last three columns represents identity matrix, and associated variables are s1, s2, s3. First 100, sorry 10, first row 100 is coefficient of s1, second 010 is coefficient of s2, and 001 is coefficients of s3. So here we take xb as s1, s2, and s3. Now we put into bxb is equals to small b. Small b is again constants, which were, you can see, are 430, 460, and 420. So we have get equations identity matrix into s1, s2, s3 is equals to 430, 460, and 420. Using the property of identity matrix, we would get this value, that is column vector of s1, s2, s3 will be equals to column vector of constants, or we can write initial basic feasible solution as s1 is equals to 430, s2 is equals to 460, and s3 is equals to 420. Now next step we construct the a special type of table which is called as simplex table. In simplex table, some specified columns and rows are used. Here first column CB represents the cost of basic variables, that is cost of variables which are involved in xb. Xb represent the initial basic feasible solution, or you can say basis in the simplex table, and solution is put in the same order as it was obtained. We have got s1 is equals to 430 in first row, so I have written s1 is equals to 430 in first row. Then s2 is equals to 460 was second, then s2 is equals to 460 is written in second row, and s3 is equals to 430 was in third row, yeah, or you can say last row. So I have written here x s3 is equals to 430, and cost of these three variables were 0 in the objective function, so cb contain all the elements as 0. cj represents the cost coefficient of all the variables involved in the our objective function, or you can say in the linear programming problem. So after basis, first column is for x1, second column is for x2, that is first three decision variables, first three column represents decision variables, and last three columns represents the slack variables. And here you can see these values written are nothing but the a matrix, that is coefficient of x1, coefficient of x2, coefficient of x3 in the constraints. Now we go to, after constructing this simplex table, we move to next step. And in next step, we calculate the net evaluation, which is denoted by Zj minus Cj, or you can write it summation Cbi Xij minus Cij. If all the net evaluations will be non-negative, that is either 0 or positive, then we said that our solution is optimum. In the situation if any at least one is negative, then we found most negative, or you can say minimum net evaluation. Now the question is how we calculate the net evaluation. So here, for calculating net evaluation, we multiply the element of cb with the element of xi, that is 0 into 1 plus 0 into 3 plus 0 into 1 minus and subtracted then the element in the cj, that is 0 into 1 plus 0 into 3 plus 0 into 1 minus 3. So all elements which are adding will become 0 and subtracted by minus 3, then it will become minus 3. So our net evaluation is minus 3. Similarly, for x2, net evaluation will be obtained as minus 2. For x3, it is obtained as minus 5. And the elements in the basis, for them, net evaluation will always be 0. You can calculate it by in same manner, multiply element of cb with corresponding element of s1 si and subtract cj from that. So here three net evaluations are negative, so we cannot say that it is a optimum solution, and we find the most negative or minimum. So among minus 3, minus 2 and minus 5 is most negative, or you can say minus 5 is minimum. So corresponding column variable will enter to the basis. That is, we said that x3 will enter to the basis. Now if it enter to the basis, some element will be replaced from that one. So which is replaced, it is decided in next step. Then for the element of basis that is constant in the basis will be divided by the elements in the column of entering variable, that is calculate the ratio xbi upon xir such that xir are greater than 0. If element of entering variable elements in the column of entering variable is 0 or negative, we cannot calculate the ratio, and in that situation we said that solution is unbounded, otherwise we calculate the ratio. Here the ratio is calculated. 430 is the x3 is entering to 4, so 430 is divided by 1, that is first element of x3. 460 is divided by second element of x3, that is 2, and 420 is divided by the third element of x3, that is 4. So we get a ratio 430, 230 and 105. So minimum is 105. We said that corresponding row variable, that is S3, will leave the basis. So we can say X3 enters and S3 leaves. That means we replace S3 by X3. Now in next step, we construct new simplex table by making leading element as 1 and all the other elements in the column of entering variable as 0. So what is the leading element? For leading element, we draw a hypothetical vertical line for entering variable. So in column of x3, if we draw a line here, this line will lie, and draw a line in row of S3 that is leaving variable, then this line would obtain. And X3 and S3 intersect at this point, that is 4. So this 4 is called as leading element. The element which is called common in entering variable and and leaving variable, that is called as leading element. This element is made 1 and all the other elements are made as 0 using elementary row operations only. So here we can make the leading element 1 by dividing the complete row by 4 from XB to S3. Always remember, operation will perform from the column of basis to the column of last variable involved in the linear programming problem. Column of CB and column of ratio is not included in the row operations. So complete column is divided by 4. We would obtain x3 is equals to 105. Here x3 enter and x3 leaves. So s3 is replaced by x3. So and first element will become 1 by 4. X2 have 0, so it is divided by 4, then it will become 0. Third element will become divided by 4, it will become 1, and so on. So first third row is obtained by dividing the third row of original simplex table. Then second operation perform is R2 is replaced by R2 minus 2 R3 dash. R3 dash is new row. Using this, the element of x3 will become 0 in second row, and operations will perform, then this row is obtained. And third operation applied is R1 is replaced by R1 minus new row of R3. So after subtracting, applying the complete column operation, this row will be obtained. And we can say this is our first iteration. As it is repeating, repetition is called as iteration. So it is our first iteration. Then here you can see in place of 0, 5 is written. So cost of x3 was in objective function was 5. So here cost of s3 is replaced with the cost of decision variable, which is 5. Again, we calculate net evaluations in same manner, and you can see two net evaluations are negative, among which most negative is minus 2. So x2 will enter to the basis. Then two elements of x2 are 0. So here two ratios are not calculated, whereas one element is positive. So that for that element divided the element of xb, that will give 325 upon 2. Since it is a single, it is treated as minimum. So s1 will leave the basis, and a column of x2 and row of s1 intersect at 2. So our leading element will be 2. So it is in next iteration we made it 1 and all the two other elements are 0. So there is no need to perform operation on other two rows. So we only divide first row by 2. So here this iteration 2 is obtained. Here again x2 replaced s1. You can see in place of s1 I have written x2. And in same manner cost of x2 is 2. So here x2 is cost of x2 is written, that is it in CB first element will become 2. Again net evaluations are calculated, and in ZJ minus CJ we obtain the first net evaluation is minus 1 and other net evaluations are non-negative. So x1 will enter to the basis. Now again ratio is calculated and minimum ratio is obtained for S2, that is 100. For x1 it is around 400 and for x3 it is 420. So you can say S2 will leave the basis. So in place of x2 in next iteration we put x1 and its cost 0 is replaced by cost of x1, that is 3. Then we apply operations here mentioned, and using this iteration, that is 3 iteration 3 is obtained. which shows all net evaluations are non-negative. That means our solution is optimum. So we can write optimum solution as x1 is equals to 100, x2 is equal to 125, and x3 is equals to 80. And put this into the objective function, then we obtained that optimum value of z is equals to 950.